Let's learn about differentials. I want to go ahead and start with these examples. So as I'm looking for the differential, I'm really separating the dy and the dx when I take that derivative. So when I do that first example, I'm going to take the derivative. So d dx of y is equal to d dx of 3x squared. So we get dy divided by dx is equal to the derivative of 3x squared. Power rule gives me a 6x. Now here's where we separate out that differential in terms of y. I'm going to multiply both sides by dx. So we end up with the differential dy is equal to 6x dx. I've got another example that I want to do, really similar. I'm going to do the same thing. So I'm going to go ahead and take the derivative of y, so dy dx, I'll just write it that way this time, is equal to the derivative of cosine 2x. Now I'm going to need a chain rule because I've got that inner layer of 2x. The derivative of cosine is negative sine, so I get negative sine, I leave the inner function. Here comes my chain rule. I'm going to multiply on the derivative of 2x, which is equal to a 2. Now I'm going to take dx. This is where I separate out the dy and the dx, and I multiply it on the other side. We end up with dy by itself is equal to negative, let's bring that 2 out in front. So negative 2 sine 2x dx, and that is the differential for this function. So we're using this formula. dy is equal to the derivative of our function times dx. But why? What does it mean? Here's an example where we've got the differential at x equals 2 with dx equal to 0.01. Well, whenever we talk about dy dx, we're talking about the slope of that tangent line. So what we're actually doing is using the tangent line to approximate a difference in the function. So for this example, we could say that x represents time, and we've got a difference in time of 0.01 seconds, and that's going to affect the outcome of this function. Let's say the outcome of this function is the path of a rocket ship. So whenever we increase time by 1/100th of a second, we are changing the path. But that change in path is going to depend on where we are in terms of time, in terms of that domain. Let's do the math on this one. So as I'm doing my differential, dy is equal to the derivative of my function. Power rule gives me 6x times dx. So as I'm solving for dy, I'm going to put in for x that 2. So equals 6 times my x value, which is 2, times my dx value, which is 0.01. So we get that differential dy, the change in the y direction. Think about that rocket ship, the change in its path at 2 seconds is equal to 12 times 0.01. That's going to be 0.12. So most likely you're going to also be asked to find delta y and then the percent error between dy and delta y. So what's the difference? dy is our approximate function difference. It's what we get off of the tangent line. So that dy is equal to the difference in the y direction off of the tangent line, call it the linearization, but that dy, we are going to be using the derivative times dx. Now delta y, that's our actual difference. This goes back and uses that function, and it's going to take the function values. Now notice that our delta x and dx are exactly the same. That's just that difference of 0.01. But in the y direction, we can approximate dy using the linearization. But why would I do that when I can just do the derivative times dx? But delta y is the actual function difference. And we know that dy is approximately delta y. Now, why do we care? We care because of computational efficiency. Computing things along a line is often way more efficient and accurate than computing things with a more complex function. If you're learning a lot, I would love it if you hit that like button. Let's go ahead and work this one out. Now, first of all, you'll remember that when we figured out dy, that differential, and that differential turned out to be 0.12 using that derivative times dx formula. We also want to figure out delta y. Delta y is my function difference between my function value at 2.01 and the function value at 2. Well, my function is 3x squared. So that's going to be 3 times 2.01 squared minus 3 times 2 squared. Computing this with my calculator, I end up with 0.1203. So I've got dy and I've got delta y, and I'm ready to compute their percent difference. I'm going to use this formula, so that's estimate minus actual divided by actual times 100 to get it into percent form. Our estimate is the dy, so this is going to be our estimate, and our actual is the delta y. So I can put this all together into my percent error. So it's going to be my estimate, which is 0.12, minus my actual 0.1203 divided by the actual 0.1203, and then times 100. So computing this gives me a really small number. I get negative 0.249%. This is after I multiplied it times 100. So I've got a really, really small error there between that actual difference in the function values and the differential that we found. You are doing great. Take a look at this video that I've got here for you next.